The subject of my talk is a hidden variable model for universal quantum computation with magic states on qubits. So that's kind of a weird thing, I suppose. It's kind of the opposite of what this conference is about. The conference is about Cauchy-Specker and about how hidden variable models do not work. And so now I am presenting to you such a model. So in the end, there will be no technical contradiction, and we'll talk about that, but I think it is useful for you to know as a reference point. So let's get into that. So maybe as a starting point, I should say, we are a quantum computation group. We are not per se quantum foundations people. So we look at this whole area of quantum mechanics foundations from a quantum computational perspective. We think there's interesting stuff there, and maybe that can be used to construct quantum algorithms. That is essentially our angle. Yeah, just wanted to say that. And now to the result. So here's a summary of the result. So we have constructed a hidden variable model with a positive representation for that is a representation by a probability function of all quantum states in finite dimensional Hilbert spaces, all Clifford unitaries, and all Pauli measurements. So you see, the states are not restricted. It applies to all quantum states. The operations are restricted. You cannot do all gates. You cannot measure everything you want. You can only do Clifford gates. You can only do Pauli measurements. However, this package here suffices for universal quantum computation. So those restrictions here, they do not show up phenomenologically. So what we say is we have a hidden variable model for all quantum mechanics in finite dimension. Okay, so that's what the result is. And so can this really be true? Because there are theorems in the literature that say you can't have it. So here is one theorem by Chris Ferry that I have just copy pasted. And it says a quasi-probability representation of quantum theory must have negativity in either its representation of states or measurements. So positive representation of both doesn't seem to be possible. It's excluded by this theorem. However, this is precisely what we say. You have positivity in both. And so how does this fit together? And the reason that there is no contradiction is in the assumptions. So this theorem here comes with a couple of assumptions. The most important of them are that the quasi-probability functions considered here are unique. So for every given quantum state, you have exactly one quasi-probability distribution. For our situation, you don't have that. So you can represent one and the same quantum states by many probability distributions. And so you need, so that's kind of the key ingredient here. So this non-uniqueness of representation, and you need to make up your mind about what you think of this. Okay, and then a further difference is that this theorem up here considers all measurements, not just Pauli measurements. Our theorem only considers Pauli measurements. However, this is sufficient for universal quantum computation. You don't need anything else. Okay, so this just kind of, I just wanted to illustrate here to you that the positive representation of both operations and states is something unusual, as this theorem says. Technically, there is no contradiction because assumptions matter. Good. So yeah, here's an outline of my talk. So it has really two parts. So the first part is that I want to give you a short history of the subject. And what is our subject? We want to talk about a particular scheme of quantum computation with magic states. We want to talk about the negativity of Wigner function. This is our quintessential resource here in this framework. And contextuality. Okay, so I want to talk about this triangle. And all of this is nice and kind of not too hard if your Hilbert space dimension is odd. So there is a big difference here between even and odd Hilbert space dimension. And I want to tell you a little bit about what happens in even dimension, specifically when you're dealing with qubits. So this is just kind of how this research developed. And then the second part of the talk is our model itself. So I want to give you what the model is and what the result is, and then how it is compatible with results in the literature. And I will, given the time, I will talk about two, the PBR theorem, but I think more importantly for this conference, the Cauchy-Specker theorem. And then I will conclude with what all of this says about the classical simulation of quantum computation and the hardness of this. Okay, so this is the program. Let's get started. So let me just define what we are talking about. So we are talking about a particular scheme of quantum computation, the so-called quantum computation with magic states. So this is a computational model that is very closely related to the circuit model. So you have gates that you can use, but you don't have a universal set. Rather, you are restricted to the so-called Clifford gates. That's the C0 and the Hadamard and those types of things. And your measurements are also restricted to the Pauli measurements. So the Goddard-Manil theorem tells us that if you just have those operations, then you're not universal and you also efficiently classically simulable. So you need other stuff. And this other stuff are the magic states. So these are non-stabilizer states, and by including them, by kind of injecting them into the computational scheme as resources, you recover universality. So you have a universal scheme again. And so this may seem as an unnecessary complication, but in fact, this is very practical. So as of now, this scheme of quantum computation, kind of restricted gate set, magic states, is the leading candidate for fault-tolerant quantum computation. But we are not concerned with practicalities here in this talk today. Fault tolerance doesn't interest us. For us, it's just a fun computational scheme to look at. And what we observe is that computational power is shifted from the gates, which are now restricted, to the states. And so a question that comes up is, which properties must the magic states have to enable a quantum speedup? And an answer that people have found, chiefly the Joe Emerson group, is that these magic states must have negativity in their Wigner function. Otherwise, they cannot be a quantum speedup. Okay, so now next thing I want to do is, if you don't know it yet, tell you a little bit about what a Wigner function is, and then explain this result to you, why you need negativity in the Wigner functions to have a speedup. Okay, so the Wigner function is a quasi-probability distribution. So it's basically a probability distribution, except it can take negative values. It is a representation of a quantum state. So it's something that describes quantum states. You can say it is the density matrix expressed in a particular basis. Yeah, so it is real valued, but can take negative values. So it is the closest quantum counterpart to the classical probability distribution over phase space. So in classical statistical mechanics, you consider phase space that would be spanned by position and momentum coordinates, and you could have a probability distribution over those if you don't know what the initial conditions of your problems are, for example. Quantum mechanically, you cannot have this exact same thing because of the Heisenberg uncertainty relation. You cannot measure position and momentum simultaneously. So that leads to changes, and the essential change is, well, you can have something like it, that's the Wigner function, but the Wigner function sometimes goes negative. Okay, so this is as much as I want to say about Wigner functions. Or maybe you wonder, maybe I should also say that. You may wonder, okay, if we have a bunch of qubits or qubits, what is position and momentum? Well, when we transition to finite dimensional state spaces, what used to be the position basis becomes the eigenbasis of sigma z, and what used to be the momentum basis becomes the eigenbasis of sigma x. But this is now really all I want to say about Wigner functions. And now, what has been shown invoking Wigner functions in quantum computation? So it has been shown that quantum computation with magic states, which is our computational scheme, can have a quantum speedup only if the Wigner function of the initial magic state is negative. So negativity in the Wigner function is a necessary precondition for quantum computation. So this result has first been shown by the Emerson group for qubits in odd dimension and has been subsequently generalized to other settings. So 2 comments about this slide. I will be focusing on Wigner function negativity, but what these people here, or some of those anyway, also showed is that Wigner function negativity and quotient-Specker contextuality are exactly the same thing in this odd dimensional setting. Okay, so there's a connection right there to contextuality. So you can rewrite this theorem and say you need contextuality for a speedup. Second thing to say about this slide is that there's lots of empty space here, and that is not a formatting glitch. There is something that goes here, and you will see that later. The slide will come up again. All right, so Wigner functions. There is important properties that Wigner functions have and that we need to talk about. Remember, I want to illustrate to you why this theorem holds. So the first important property is covariance of Wigner functions. So, okay, so here you have a peaked Wigner function, say, and you're now applying a Clifford gate to that corresponding state. And what you'll find is the Wigner function, the peak just shifts to another location. So that is remarkable. Why is that remarkable? So imagine you would be doing that with a non-Clifford unitary, and then what you would get instead would be some scattered mess. Yeah, so the sharp peak would not move to another location, but it would turn into some scattered mess. Yeah, so with Clifford gates, this is fortunately not the case. So the peak just shifts, and this is what the covariance condition tells you. So this is going to be a very important property later on. So please keep in mind that covariance matters for our entire discussion, and we'll see shortly why. The second property of Wigner functions that we need to talk about is preservation of positivity under Pauli measurements. So again, we are looking at a peaked Wigner function. It is not a Wigner function, not a physical state anyway, but it's something that we can look at from a mathematical perspective. And so, so what we find is if the state represented by that peak is subjected to a Pauli measurement, then it remains positive. So what we are getting is, as the post-measurement state, is this ridge. So the Wigner function is non-negative only on a line in phase space, and it is, yeah, so it's non-zero only on a line on phase space, and it remains positive everywhere. And also these peaks all have the same height along the entire line. Okay, so this is so positivity preservation on the Pauli measurement is another important property of the Wigner function. Okay, and so now we can explain this result, how it works. So we wanted to show that you need negativity for a speedup. And so the contrapositive of this is to say, okay, our initial Wigner function is positive to begin with, and then there's no speedup. And we show this by explicitly constructing an efficient classical simulation algorithm. And here you see how it works. So the initial step of the simulation algorithm is that you sample from this Wigner function. So it is now, by assumption, a probability distribution. So with a bit of extra luck, you can sample from this. And that's how the simulation algorithm starts. And then what you then subsequently do is to follow this sample through the sequence of operations. And remember, in this computational scheme, every operation is either a Clifford unitary or a Pauli measurement. And all of this is easily followed. So if you are dealing with a Clifford unitary, you're just updating the location of that peak. using covariance of the Wigner function. And if your next operation is a Pauli measurement, then you're using positivity preservation of that Wigner function. So you basically can simulate Pauli measurements with a coin flip. Okay, so that's the idea without going into technical detail. So if the Wigner function becomes negative, this simulation algorithm fails at the very beginning. You can't sample from that distribution anymore. Good. So this is about that theorem. Let me just say one more thing about negativity. So this is now an extension of the earlier theorem, and this is work by Cooper, Shayan, and company. So we can ask the question, so now if there's negativity in the initial Wigner function, how quickly increases the complexity of the simulation with the amount of negativity that you have? And that's the content of that theorem here. So O is the operational cost of classical simulation. And here in the expression on the right-hand side, you have the one norm of the Wigner function of the initial state. And you see, so negativity in this Wigner function drives up the one norm because you still have the normalization condition. So what it means, if you have negative peaks, then you also have large positive peaks. And because you're taking absolute values, that blows up the one norm. And it can be shown that the cost of simulation increases quadratically with the one norm of the Wigner function, which is just a measure of negativity. Okay, further, it is numerically shown and analytically upper bounded that if you have the Wigner function of a magic state raised to the nth tensor power, the negativity or the one norm scales exponentially in n. Okay, so you plug this in here and get an exponential increase of complexity. Good. I just wanted to show you that negativity in the Wigner function is, in this way of simulation, the reason why the classical simulation becomes hard. Okay, so that's another thing to remember for later. Okay, so now that was all for odd dimensional systems. So now the trouble with qubits. Where does it come from? So the Wigner function is a construct from quantum optics. So it naturally lives in infinite dimensional Hilbert spaces. And quantum computation lives in finite dimensional Hilbert space. So you need to make the transition from infinite to finite. If your finite dimension is odd, this transition is really easy to make. But then if you go from odd to even, all hell breaks loose. And the reason why this is so are these little monsters here, Mermin square and Mermin star. And I don't have the time to go into explaining this connection in detail, but this is really where all the problems come from in even dimension. Okay, and so it starts with covariance. So let's not get ahead of myself. So let's just kind of define the object that we're looking at. So here's our density matrix, say, of the initial state of the magic state, and we are expanding it in a certain way. So we're expanding it in terms of phase point operators. It's just a bunch of operators that span the space of Hermitian operators. So those operators have a label. So there's a bunch of them, and we label them. And those labels are points in what we call phase space. So much about these operators. And the expansion coefficients we call the Wigner function. And so now an important distinction arises whether these operators, whether they form an operator basis, that is, they are minimal, or whether they are not minimal. So maybe a priori you want them to be a minimal set, you want them to be a basis, but if you require that, then it has been proven that the corresponding Wigner function cannot be Clifford covariant. Cannot be Clifford covariant. And remember, Clifford covariance was essential for us in establishing the theorem. So now the question is, what do you do with that? And the lesson that we have drawn from this situation is that we base our quasi-probability function on an over-complete set. So we ditch the requirement that those guys need to form a basis. So we'll have an over-complete set, and that makes our Wigner function, our quasi-probability distribution, redundant. Okay, good. And so if you're prepared to make that step, if you're prepared to give up uniqueness of your quasi-probability distribution, then all is good. Then you can reestablish for qubits exactly the same picture as you had for qubits earlier, that is for odd dimension earlier. The price to pay is that you have an over-complete set now, and your phase space has kind of a very complicated structure. It's no longer a simple grid that you can travel by translation. Okay, but if you're willing to pay that price, then you can establish exactly the same result that Emerson and company had established earlier in odd dimension. But that is not the purpose of this talk. Let's move on to the purpose of this talk. And now you see this earlier slide again. So the purpose of this talk is to make a counterpoint. Okay? So the above results here, Emerson's results and all that came afterwards, they rely on a particular definition of quasi-probability distribution. And if you generalize this slightly, and really the only generalization you need is to go away from uniqueness. If you admit this slight generalization, then the need for negativity entirely disappears. Entirely disappears from the operations and from the states. And this is the thing that I want to talk about, the counterpoint. Good. Okay, so here we go. We talked about the counterpoint, and there's 3 parts in this section now. Good, I'm going. So there's 3 parts here in this section. So we have the model and the result. We have questions of compatibility to discuss. So there is the PBR theorem and the Cauchy-Specker theorem. And the question is also, what does this mean for classical simulation? Good. So let's talk about the model. And before I go into the definition, so this is the definition of state space, the most important thing here on this slide, but I want to tell you what the motivating question was that led us there. And so the motivating question is, for any number of qubits, what is the largest state space that preserves positivity on the Pauli measurement, that is closed on the Pauli measurement? Okay, so I'm tinkering with this question leads us to this definition of state space. So what do basically our states are Hermitian operators. So it's first condition, they have to be Hermitian. You know this from density matrices, so no difference here so far. They have to have trace 1, also familiar looking. And furthermore, if you take the trace inner product for every such state in this state space with the projector onto a stabilizer state, then this inner product has to be larger or equal to 0 for all stabilizer states. This also looks familiar because that's very closely related to positivity of density matrices. So in fact, for density matrices, you would enforce something stronger. You would have this condition hold not only for all stabilizer states, but for all states. And so this immediately shows that the states of all density matrices are included in our state space for any number of qubits. So all of quantum mechanics, as far as the states are concerned, are in it. Also, what we need to say is that our polytope can be described by its external vertices. And so these vertices, they have a label, and the set of these labels forms our generalized phase space. This is what we call phase space in this context. And the point to make is that our phase space is finite for all numbers of qubits. Good. Okay, so now here is the main theorem. Everything is positive. So this applies to the states. Quantum states are positively represented by probability distributions over these extreme points. Positivity is preserved on the measurement, and also the Born rule is positively represented. That is, if you have a density matrix or quantum state rho, you measure a Pauli observable with a given outcome, then the probability of getting this outcome is given by this formula, invoking probabilities and conditional probabilities. Nothing negative ever occurring. Good, so everything is represented positively. Okay, so so that maybe I should say a little bit about the proof of this. So this part I already talked about. This positivity of states is this diagram. Maybe I talk a tiny little bit about this. Okay, so what we want to show is the following. So what we want to show is that if, say, we have an extremal vertex, and now we sandwich it with projectors corresponding to a Pauli measurement, that this is a probability distribution over extremal vertices. Yeah? And so in other words, this is contained in the state space. Good. Okay, and so this is how this would be done. It's kind of a very simple argument. So this is our assumption. The vertex is in the polytope. It's an extremal point of the polytope, so it's in the polytope. And now from this, we want to show that this sandwich is also invoking the object after the measurement. We want to show that this is also positive. And this is a very simple argument, just involving the cyclicity of trace and associativity, and furthermore, a little bit of stabilizer theory. So when you have a stabilizer state and apply a Pauli measurement, this gives you another stabilizer state. So that is basically the argument.
Robert, that's 3
Yes.
minutes. You have less than 3 minutes.
How many?
Less than 3.
Okay, good. Okay, so then let me move on. Clifford unitaries is the same story. I have no time to explain it in detail, but what we now have shown is that we have all the operations we now have together to show that universal quantum computation by Clifford unitaries and Pauli measurements on magic states can be described by an iterated sampling of probability functions. Okay? Again, universal quantum computation positively represented. So this is about universal quantum computation, hence all quantum mechanics in finite dimensional Hilbert spaces. Both operations and states positively represented, no claim of efficiency after simulation. Okay, so now, what is the big question here? So negativity has been eliminated. And so but it previously was the reason for the hardness of quantum computation. And so if it's not negativity anymore, then what makes the classical simulation by sampling hard? So that's kind of the main open question right here. And that's what I want to leave you with. But because I probably have a minute or so left, let's just talk about consistency with quotient spectra. So let's just kind of make clear what we have shown. So as a very special case of our simulation scheme, you could go through a sequence of measurements in the Mermin square. And you would never, ever detect a discrepancy with quantum mechanics. So, and this is all done with a hidden variable model underneath. And so why is this not a contradiction with quotient spectra? It's not a contradiction with quotient spectra because the value assignments in our hidden variable model are probabilistic, not deterministic. So quotient spectra doesn't apply. Good. One last comment. What can be classically simulated or efficiently simulated? I said this is by and large open. But at least you can efficiently simulate everything that is in the domain of the stabilizer formalism. So that's a starting point. We know that we can simulate more efficiently, but we don't know how much more. And maybe this is a good end on which to end my presentation.